A very good day. My name is Vignesh with metric ID MA20019. I will be introducing to you our lab experiment, which is the Pelton wheel turbine. Before we proceed, I would like to introduce my group mates. As you can see in the slide, these are my group mates. Moving on to the introduction, a Pelton turbine, sometimes known as a Pelton wheel, is a form of hydro turbine that is commonly seen in hydroelectric facilities. For sites with heads larger than 300 meters, these turbines are often employed. Lester Pelton invented this type of turbine during the 1880 gold rush. In a Pelton turbine, the water is rushing swiftly, and the turbine harvests energy from it by slowing it down, making it an impulse turbine. A water reservoir is normally situated at some height above the Pelton turbine when it is used to generate energy. The water then travels via the penstock to a specialized nozzle. This delivers pressured water to the turbine. The penstock is equipped with a surge tank that absorbs abrupt changes in water pressure that might cause pressure anomalies. The Pelton turbine is an impulse turbine as opposed to other types of turbines that are reaction turbines. This simply implies that instead of moving due to a reaction force, water causes the turbine to move by creating an impulse. Impulse turbines work by converting the head's velocity via a nozzle into a high velocity that impacts the buckets in a single place as they pass. Because steady pressure jet travels through the buckets, the runner passageways are never completely filled. These turbines are well suited to low power high-end derivations. The stationary input nozzle, the runner, and the casing are the three essential components of the Pelton wheel turbine. The runner is made up of many buckets. They are mounted on a wheel that spins. They are designed in such a way that they divide the flow in half and spin in a nearly 180-degree velocity vector. Moving on, our problem statement is to determine the ideal size of wheel to use, how quickly it should revolve for maximum efficiency, and our objective is to find the necessary data to assess the performance parameters of a Pelton wheel hydraulic turbine. Torque and power is given as the data. Finally, the scope of our experiment is to investigate the Pelton turbine's constructional features and performance metrics and test the theory that states a Pelton wheel turbine is most efficient when the speed of its bucket is half that of its water jet. That is it for the introduction. I will pass the presentation to my friend for the theory of our experiment. Thank you.
Assalamualaikum warahmatullahi wabarakatuh, and my name is Muhammad Syafiq bin Maksuf, and today I will present about Pelton turbine. So Pelton turbine is known as a Pelton wheel because it's normally seen in hydraulic plant. So water reservoir is normally placed at some point above the Pelton turbine when it is used to generate energy. Water turbine is an impulse turbine because when there is action, then it will be reaction. Pelton turbine theorems. So the turbine will turn the water head into high velocity jet through a nozzle. It will because the runner tunnel are not completely filled. The jet flow past the bucket is basically continuous. The equation is applied to the control volume yield the power taken from the available head by the turbine. Assume that the outgoing jet's speed is zero and that there is no head loss at the nozzle or the impact with the buckets. So there is three types of efficiency in Pelton turbine. So the first one is hydraulic efficiency. It is the ratio of the power generated by a turbine's runner to the power supply at the turbine's inlet. So the formula is NH equal to runner power divided by water power. The second one is mechanical efficiency. So it is the percentage of the shaft power to runner power in a turbine, based on mechanical issue that cause the energy loss between the runner and the annular space between the nozzle and spear. So the formula is Nm equal to shaft power divided by runner power. And last but not least, the overall efficiency. It is the ratio of a turbine's usable power to the power delivered at the inlet. It encompasses all energy related issue. It depends on both hydraulic loss as well as slippage and the other mechanical issues that cause energy loss between the jet power given. And the formula is water shaft divided by water power. And that's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. Hi, my name is Muhammad Azim Hamidi. So for today, for this lab, Pelton Turbine, I'm going to present about the methodology of Pelton Turbine in Engineering Fluid Mechanics lab. Okay, first of all, we're going to discuss about the experiment setup. First, we make to make sure all of the connections are secure and there is no water leaking before starting the experiment. Plus, no braking device has zero load because it will cause the experiment to stop. The third one is what we need to find the flow rate from hydraulic bench. Then we need to use the data for the Pelton turbine calculation. The fourth point or the fourth step is to rotate the nozzle valve axially by turning null cap. A scale on the cap is used to determine the nozzle position. Finally, we need the jet has to be centered by the adjuster sleeve with a WAF10 wrench to spread the water equally over both sides of the blade. So these are the setup for the Pelton turbine experiment. Then we move to the equipment and materials. For Pelton turbine, there are 5 equipment to be used. For example, manometer, nozzle adjustment, nozzle, Pelton wheel, and brake adjustment. Based on figure 3.1, it shows the Pelton wheel turbine that we're going to use with the type of HM 150.19. The next one is about the hydraulic bench. The hydraulic bench consists of 6 parts, which are flow control valve, overflow, storage tank, pump, valve, measuring tank level, and measuring tank. Figure 3.2 shows the hydraulic bench that we're going to use in this experiment. Okay, figure 3.3 until figure 3.6 shows about the example of parts or equipment that we're going to use. For example, tachometer, speed controller, pressure sensor, and flow sensor. Okay, next we move to experiment procedure. After we setting up our experiment based on the previous section, we need to turn on the pump and set the stopwatch to 0. Then we need to close the valve at the bottom of the volumetric tank and wait until the liquid reaches a value of 10 liters, and at the same time start the watch. 60 seconds is the minimum measuring period. So after we set up the time which is the 60 seconds, we need to start the stopwatch when the water level reaches 10 liters after closing the valve at bottom of the volumetric tank. The fourth step is about after the liquid reach a value of 20 until 30 liters. We need to stop the watch and read the results or the measurement time and the high value of water in tank. The fifth step, we need to calculate by using the formula as shown in the slide, which is to calculate the flow rate from the tablet data. Okay, then after getting the data and after we done the calculation, for the plotting of power curve, place load on the turbine in increment of 0.5 Newton by way of the brakes at various nozzle position and record the braking force and rotational speed, which is the RPM. And then the next step is keep fall height at a constant 0.2 bar, which is 2 meter, by means of the ball cock in the HM 150 inflow and reading from water column. Then we need to calculate the volumetric flow for each nozzle setting using the equation below. After that, each of interval record the speed using an optical tachometer and both spring balance forces. Then we need to calculate the power of the turbine shaft. Furthermore, hydraulic power is a function of the volumetric flow and fall height. If fall height is kept at 2 bar and 2 meter, we need to cap the height at 2 bar and 2 meter. Then we need to determine the efficiency of the turbine and record on table 2 and table 3 as we get in the Pelton turbine report. All readings and the graph need to be drawn based on the RPM, power output versus RPM, and efficiency versus RPM. Finally, draw graph power output versus RPM for different nozzle position. So that's all from me for the methodology part in this lab. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Atifah binti Mazri, Metro ID MA19308, and today I will present about the for leg 5 results, which is the Pelton wheel. Next. Now we have the characteristic curve table. What we have here, the given data is rotational speed, braking force, moment on the shaft, power out, power in, and the efficiency. The efficiency without shaft steering here, we define it by using this formula, which is the power out versus the power out divided by power in times 100, and we got the percentage of the efficiency here. Next. We have the power curve table. There's braking force in Newton, rotational speed in RPM, and then the power out in watt. Next. Okay, here we have the graph of the torque versus RPM. We can say that this graph have a linear positive relationship, which is when the torque increase, the rotational speed in RPM also increase. Okay, now we have the graph of power output versus RPM. We can say that this graph have the curvilinear relationship between the power out and rotational speed. From me, thank you. Now let's proceed to the discussions.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Aiman Jufri bin Muhammad Safi. ID's number is MA203. Okay, my part is discussion Pelton ways. Okay. Okay, for the question 1 is graph torque versus rotational speeds. Okay, we can see the rotational speed. If the rotational speed faster will be faster, so the moment on the shaft can be decreased. Look the graph at that. For the question 2 is graph power outputs versus rotational speeds. We can see for the rotational speed C130, we can see the power out is 4.8. It is better than from rotational speed 286 and power out is 4 watts. Okay, for the next slide is question 3 and question 4. Question 3 is what is the maximum torque produced? At 286 rpm, the Pelton will produce maximum torque which is 0.1325 Newton per meter. The torque is maximum when the runner is stopped when Q equals 0 and T is your velocity. When the speed of the runner is equal to the initial jet velocity, the torque is 0. Okay, number 4 is what is the maximum power output from shaft with constant nozzle? At 470 rpm, the Pelton wheel turbine produce the maximum output from shaft with constant nozzle, which is 3.2 watts. For the question number 5 is what is the efficiency for the turbine? Each Pelton bucket must be hit exactly in the middle by the jet as previously stated in the design of the buckets. The spinning of the turbine is dependent on the velocity of the water jet. The efficiency is determined using both formula P out over P in. Based on the result of the experiment, as a result, the turbine efficiency is determined by its power output. Pelton turbine can achieve a maximum efficiency. Question number 6 is what is the maximum power the turbine can produce? The turbine maximum power output is 5.6 at 464 rpm is the higher the input power. As a result, the power output is determined by the turbine wheel power input. Number 7. Which nozzle position the lowest power? There is a rise in velocity and a fall in pressure in a conventional nozzle, yet we know that pressure is inversely proportional to area. The goal is utilizing a nozzle is to accelerate the flow so that critical or sonate condition can be achieved at the throat. As the pressure differential between upstream and downstream the nozzle rise this happen. Okay, this all from me. Thank you.
We have finally reached the ending of our presentation. In conclusion, we can deduce that the performance of the Pelton wheel turbine is influenced by a wide variety of flow rates and rotating speeds. The power or work input is manipulated by the jet velocity, which determines the work output, which is power or output in watts. The higher the nozzle jet's power input, the quicker the flow rates, but the lower the power output. As a result, we require the ideal blend of the two. In general, an impulse turbine is a device with a high head and a low flow rate. As a consequence of the outcome, we might conclude that our experiment was a success. That is it from us. Thank you.